Hello everyone, my name is Dr. Hemlata, and in this video I will show you how to apply a linear regression model to the given data set in R. So for this here, just to save the time, here I have written all the codes here, but I'll explain one by one each and every code with the interpretation. So first just have a look on the data set that we are going to use. So here is the data which in this the weights and the systolic blood pressures of 26 males between the age group 25 to 30 are given, and the questions that on which we are going to work with are: we have to plot a scatter diagram, we have to fit a regression line between the systolic blood pressure and the weights, and also we have to obtain the fitted values and the residuals. We have to obtain the coefficient of determination and the 95% confidence interval of the regression coefficients, and we will also interpret the results. So as we are going to work in R, so for this we will just copy and paste this data in the Excel file, and we'll make a different Excel sheet of this data set so that it will be easy to import the data in R. So as you can see here, I have already pasted this data in Excel like this. So I have already saved this file with the name slrm data. Now we are going to work in R. So just because our data was in Excel, so we have to import this data set from Excel sheet. So for this we need a one package, that is read Excel. So for this code is used to install the package. Install.package is read Excel, and once it is installed, we have to load the files of the read Excel package. So we'll use the library function to load it. So we'll run these two codes first. After installation and the loading is done, we'll import the data set. So just to import the data set, what we'll do, we'll go to the files, and then we will click on the import data set, and then we will click on from text read R, or you can click from Excel. So by both these links you can import the data set. So here I'm going to click on from Excel. So you'll get this, you'll browse. So now you will go to the folder where your data file is saved, the Excel file is saved. Here I have saved the data in our video content, and my data file name is this. So I'll open this, and once this retrieving preview data is done, what you have to do, you have to copy this code, and or you can just copy this code so that if you are going to make a report, it will not bother you to create a report just to get the PDF file or just to get the output file. So we are just copying it and importing this also. So as you can see, when we have imported it, your new data file, the data file has opened here, but the same code that I have copied, I have pasted here also like this. This is same file that I have copied. So this is the same file. So I'm going to remove this because this is the two times, this pasted two times. So once you have imported the data set, what we are going to do, we'll see in the folder in which we are going to work with. So this is the getwd. By the getwd you can see the path in which your work is going to store. So if I run this getwd, you'll see by default it has taken this folder, documents folder. Everything will save in the documents, but let's say I want to change this the folder. So I want to save all my files in R video content folder. So I will set this the directory by setwd command, and for this I will write the path. So how to get this path, let me show you. I'll go to the folder in which I want to store my content. So let me show you. Here this is my folder, our video content. I'll click on this, and I'll take the location of any of the file which is saved in this folder. So I'll go to the properties, and then here you can see the location of this folder. So I'll copy this location, and then I'll close this. Now my work is done from this. Now I'll go to the RStudio, and then I'll use the setwd, like this, setwd. In the setwd, you'll paste the location in double quotes like this. So here, if you will run it as it is, you will get an error like this. So this is the error. You can see it is not setting the path yet. So what we'll do, we will put double back symbols, double back dashes instead of single back dashes. Like you can see the change. I have put double back dashes instead of single back dashes. Now if you'll run this double back dashes, then it will set the directory. Now I'm going to remove this. This is my correct one. So after this, if you want to check whether your location has changed or not, directory has changed or not, you can run getwd again. You can see now your path has changed. Now your work will save in our video content folder. So previously it was document. Now after changing it, it has become this one, our video content. Clear? Now let us attach our data set. So I'll use the attach function for this, attach function, and the data file name. This is my data file name. Here I have stored the data. So I'll run this also. It will attach the data. It will give few information about this, like that there are two columns, SBP and weight. Now I want to draw a scatter diagram between SBP, the systolic blood pressure, and weight. So for this I will use the plot function. In the plot I will write the variable x name and the variable y name. So in our data set, as it is obvious that the systolic blood pressure is depending on weight, so weight is our x and the response variable is systolic blood pressure, that is y. So if I run this, I'll get this scatter plot, as you can see in the right hand side. So by the scatter plot you can see it is having some increasing trend like this. So from this it is clear that there is a positive relationship between the variables weight and systolic blood pressure. Still if you want to know what is the degree of relationship between these variables, so you can use the core function. It will give you the Carl-Pearson's correlation coefficient. So I'll write the core. In the core function I'll write the variable x name and the variable y name separated by comma. So if I run this, you will get the output, that is the correlation coefficient is 0.077. so you can interpret the this result like there is a strong positive correlation as this value is quite close to 0.8. so there is a strong positive correlation. This indicates the degree of linear relationship between the weight and the systolic blood pressure is strongly positive. So now once it is clear that the variables are correlated, we'll fit a regression line between these two variables. So to fit the simple linear regression model, here you can see if I'm writing any text, so I'm writing with the hash sign. So if you write anything with the hash sign, it will be considered as a text. here in the RStudio, right? So now let us run the linear regression model between the systolic blood pressure and the weight. So for this we'll use the LM function. LM function is used to fit a simple linear regression model between two variables. One is dependent and one is independent variable. So here I want to store my results in the model. This is just an argument name. You can give your choice name. So I have written the model because it is going to create a model. So in model my result is going to store. So here this is the assignment operator. This will assign the values of this function in the model, and the model is LM. In the LM here, SBP is the dependent variable. So first you have to write the Y variable, the response variable. In my case it is the the systolic blood pressure, and followed by this curly sign. Curly sign is showing the dependency. So this systolic blood pressure is depending on the weight. So SBP, curly symbol, and the weight, the x variable, right? So this sign, the curly sign, you can get in the keyboard just above the tab key. If you can see this sign, you can find this sign. So this is the command for the linear regression model. If I run this, see your code has run but you didn't get anything. So to see the results what has stored in the model, you have to type the model again and you have to run the model, then it will give whatever is stored in the model. You can see this is the formula that we have put, and these are the regression coefficients. So from this you can find your regression line, linear regression line. So the intercept is your beta naught. So your regression line will be the SBP, systolic blood pressure, is equal to beta naught, that is 69.1044 plus 0.4194 into weight. This is the beta 1. So this is, if you want to know more about the model, then you can use a summary function. So in the summary I will write the model name, that is my model. So if I run this, I'll get a lots of information about my regression model. So this is what is the formula of the simple linear regression model. If you see this block of the residual, you can see the minimum and maximum values of the residuals. So from this you can see there is a big difference where the range is too big. So this is not a good indication for our model. It is showing that there is a big difference between the observed and the expected values of the response variable. So this is not good for our model. Secondly, if you go to the coefficients block, so in the coefficients you can see again you got the intercept and the beta 1. This is the beta naught, the coefficient beta naught value is this, estimated beta naught is this, and estimated beta 1 is this. So from this you can create a regression line. You can fit a regression line, and these are the respective standard errors of the regression coefficient. This is the standard error for beta naught, this is the standard error for beta 1, and these are the p values for beta naught and t values. So t statistics, this can be obtained just by dividing this beta naught divided by its standard error. If you will divide this value divide by this, you will get this t statistic. So similarly you can get the t statistic for beta 1 also. So if you will divide beta 1 divided by the standard error of beta 1, you will get the t statistics. But we are interested in their p values, so these are their respective p values. We are more interested in beta 1 because in case of simple linear regression model, our null hypothesis to test whether the independent variable is significant or not. Independent variable is significantly influencing our dependent variable or not. We'll see the p value. Here you can see it is too tiny. You can see this value means e to the power minus 0.06 means the value is very close to 0. The value you can see it is the 5 times 0 means 0.5 times 0 359 like this, so it is very close to 0. So if we compare it with 0.05 at the 95% of level of significance, it is less than 0.05. So in this case we fail to accept the null hypothesis, and a null hypothesis H naught is beta 1 equal to 0, means the weight has not any significant impact on the systolic blood pressure, but we are rejecting it. That means our H1, the alternative hypothesis, is accepted. In that case means this is significant, means the weight has a significant impact, significant influence on the systolic blood pressure. And if you can also see if the values are significant at the particular level of significance. Here it is significant at the 0, highly significant, it is very close to 0, right? So next, if we come to the residual standard error, the residual standard error is 8.681. It is too big. Standard error, it gives the deviation of the residual terms from its mean value, right? So mean of the residual is 0. So this is the average deviation of each and every. This is what we have seen. The range of the residual is too high. So same thing it is going to give you. So here residual standard error is too big, that means there is a big difference, means the values have the big deviation, much deviation from its mean. And if we look at the multiple R squared, this is just the coefficient of determination, and the value of coefficient of determination is 0.5983. It is approximately 0.6. So this means approximately 60% of the variation in the dependent variable is explained by the independent variable, and in our case we can say 60% of the variation in systolic blood pressure is explained by the weight, and rest of the 40% is due to the error, or it may be due to the another variables which have been not included in our model. And this is just adjusted R square, so we are not interested in this because we are dealing with the simple linear regression model. We look at this in case of multiple linear regression model. Okay, so here we will see only the multiple R square. This is the coefficient of determination. And if we look the F statistic, and the value of F statistic is this, these are the degree of freedoms of the F statistics, and this is the respective p value, and by the p value you can see it is too small, which is less than 0.05, and in that case the null hypothesis is H naught is equal to beta 1 is equal to 0. By this also you can say the regression model is the best fitted to the data. That means the weight has a significant impact on the systolic blood pressure. Now after interpreting all the results of the linear regression model, our next question was to obtain a 95% confidence interval for the regression coefficients. For this we will use the function conf_int. So if we use conf_int and the model name, that is our model, comma, level is equal to 0.95. so if you will write level is equal to 0.95, it will give the 95% confidence interval. If you want 99%, then you can write 0.99 like this. But here I want to find the 95% confidence interval, so I'll write 0.95 here. So if you run this, you'll get the 95% confidence. This is your lower limit, this is your upper limit. So we are interested in the confidence interval of weight. So this is the lower limit for the 95% confidence interval, this is the upper limit. So by this you can say the average value of the beta 1 will lie between this range, from this to this. So this was the confidence interval for the beta 1. and this is the confidence interval for beta naught. Right, so after this if we are interested to find out the fitted values, the estimated values of y, so for this we will use the fitted dot values function and the model name, and we will store these values in the estimated est underscore y. So this is just a notation. You can write anything, y hat or y estimated. I have written estimate est underscore y. So my fitted values are going to store in this. So if I run this also, you'll get your estimated values like this. So these are your estimated values. If you want to sum all the estimated values, you can use the sum function. If I run this, you can see the total of all the estimated values is this 3786. So one of the assumption, if you want to satisfy that sum of all the estimated values should be equal to the sum of all the observed values, so let us sum the observed values also. So these are the observed values of y. So you can see in the output the sum of the estimated and sum of the observed is same. So this assumption is satisfied here. So next, if you want to find out the residuals, the each error term for the each yi values, so I will use the residuals function for this, and the residual will store in the resi. This is just the name of the object. So I'll use the residuals and the model name. So if I run this also, these are the residuals. So first error for the y1 x1 is this, second error term is this, third error is term this. So if you want to know what is the sum of all the residuals, it should be 0. So if I sum the residuals, you can see it is too small, means 0.15 times 0 4 like this. So it is very small, so it is approximately equal to 0. So this assumption is also satisfied. So now this was all about the simple linear regression model in R with the interpretation. And if you want to create a report on this, you can create by using Rmarkdown. And for creation of report, I have already made a video on this. If you want to see that, I will share the link in the description box. You can go through that, and you can make the report of your R code with the output and with the nice interpretation. And guys, if you liked my video, if you found it useful, kindly please like and subscribe my channel. Thank you.